All right. In the last class, we were talking about the ideal gas at a fixed volume. Okay, and we got in the end to the equation that's on the slide there, right, on the whiteboard, right? So an equation for the free energy of an ideal gas at a fixed volume. All right. Now, in this class, I want to generalize now to an ideal gas at a variable volume. Okay. So suppose that the volume is free to change. Okay, so an example would be just a bag, right? Here's my high-tech example. Right, I put a certain number of molecules in the bag, and then it could be a big volume, it could be a little volume, right? So there is a container that can expand or contract, right? A container can change its volume. Typically, someone imagines a cylinder with a piston that can go up and down, sort of like this, right? And so there's a volume V inside, but the piston can go up and down, and so the volume can change. All right. So now there's an extra degree of freedom, right? So if there were a fixed volume, as we had on Monday, right, there are 6n degrees of freedom. Degrees of freedom. That is for the positions and momenta of all the molecules. All right. But now, if there's a variable volume, there are 6n plus 1 degrees of freedom, right? That is, there's the extra volume degree of freedom. So if you want to specify what's a state, you need to say all the positions, right? All the momenta and the total volume. Okay, now suppose we want to follow the same kind of procedure that we did with the magnet. That is, we want to classify microstates into macrostates. All right. So we're going to do this classification problem once again. And in the Ising magnet, I was classifying the states based on the total magnetization. That is this order parameter M. All right. Now, in this problem, I want to classify the microstates into macrostates based on the volume. So this will be based on volume, right? So all the microstates with the same volume get classified into a single macrostate. Okay. And so then I can say, there's a macrostate with a volume equals 1 liter. And then there's another macrostate with a volume of, 1.13 liters, and so forth, right, for all the possible volumes of the system. Right? So now we can say, following the same procedure that we had with the magnet, we want to know what's the free energy for each macro state. Okay, so we want the free energy for each volume. So, good news. That's what we already did. Okay, so we should be able to just copy over the result that we already calculated for the free energy for a system with fixed volume. Let's see, can I paste it again? Let's find out. Ooh, it works. Okay, so there it is, right? The free energy for a system with fixed volume. Okay, so we could say this is F of V, right? It depends on volume, and it has a dependence on volume just right there, okay, and nowhere else, okay? So it has a logarithmic dependence on the volume. Okay, now you remember when we were dealing with the magnet, right? The next step was to say, let's find what's the optimum value of the order parameter M, right? The best possible value of M that gives the lowest possible free energy. Okay? So let's try the same thing here. And so we want to know what value of the volume gives the lowest possible free energy. So let's make a plot of it. Okay, so I'll make my plot. Oops, wrong pen. Okay, so if I'm going to plot f of v, right, and so my function, ooh, I'll paste it again. Okay, so my function, this one, this is, it has a logarithmic dependence on volume, right? And so this is minus ktn, that's an n, minus ktn log volume plus a constant, right? Because the log of a product is the sum of the logs. Right? So it is a negative something times the log of the volume. Right? And so we know what a log plot looks like. And so we just have to turn it upside down. Okay, so an upside down plot of a logarithm looks like this. And the important thing to notice is that it does not have a minimum, right? It just keeps on going down, right? As the volume gets bigger and bigger, the free energy gets more and more negative. It doesn't have a minimum, or we could equivalently say that the minimum is at v goes to infinity. So this looks bad, right? Because we were thinking that we're going to find an optimum volume, and here the optimum volume is that infinity, right? So now we say, what's wrong with this? Okay, what did we leave out from the calculation? Okay, and the answer is we forgot about the pressure, right? We say, oh, I forgot the pressure, right? And so the point is, right, that when you have a system that is able to expand, right? When it expands, it's pushing against something, right? There is some ambient pressure out there, right? So in the picture of a cylinder, like this cartoon, we would say there is some pressure, P, that's pushing down on the piston, which resists expansion, right? And without that, then, you know, the optimum volume really would be infinity, right? If you release a sample of gas in outer space where there is no pressure, yeah, it really would expand and to size infinity, right? There'd be no limit on the expansion, right? But typically we care about what happens under fixed pressure. Okay? So that means that there is something extra that goes into the free energy. That is the energy of pushing against the pressure. There is some extra energy of plus pressure times volume. Okay? That is something which resists this expansion. So the thing that we want to minimize is not the free energy by itself, but the free energy with this extra term, okay, that represents the interaction with the pressure. Okay, so we want to minimize not just the free energy, but the free energy as a function of volume plus the pressure times the volume. This combination gets a special name in thermodynamics. This is called the Gibbs free energy and is written with a capital G. So Gibbs free energy. Okay. This is something that you know, some of you might have seen in classes, perhaps in chemistry classes before. You know, it's often introduced in a very mathematical way of saying, you know, you can have a function of volume or you can have a function of pressure. I prefer to introduce it in this sort of physical way, the sort of Homer Simpson style of saying, oh, I forgot the pressure, right? And so this is you know, what it comes down to. So now we have the Gibbs free energy to minimize, okay? And so it then is the combination of the free energy and the pressure volume term. So now let's try to make a plot of that. So I have the previous plot of the free energy. And now I want to add the pressure volume term. Okay. So as a function of volume, here is the Gibbs free energy. Okay. So at small volumes, well, this pressure volume term is very small, right? So it's going to be the same thing as the free energy. So it starts off going down like that. Okay. At large volumes, the pressure volume term, the PV, this is going to be really big. Okay. And, you know, this logarithmic term is going to negative infinity, but this term is going to go to positive infinity. And it goes to positive infinity faster than this one goes to negative infinity. So it dominates, right? The linear term is dominant over the logarithmic term. So you must have something which is increasing linearly over there. And in between, these things have to connect up and they make a minimum. Okay? So this will then be the minimum of G of V. So suppose we want to calculate it, okay? So let's go back to our equation, okay? Okay, so if this is F, then I'll change it to G. G is all of this stuff plus pressure times volume. Okay, why did I put that in the middle? I should put it at the top. Oops. Ooh, I love my lasso. Okay. All right. So G is that, right? So if I want to calculate where is the minimum, I can do it in the usual calculus way. I'll take the first derivative and set the first derivative equal to 0. Okay, so the derivative of G with respect to volume is minus KTN, and then the derivative of the log is 1 over V. And then plus the derivative of the pressure volume term is just pressure. So that equals 0. So I want to solve this for volume. Luckily, that is not too hard, right? And what we get is that the pressure is KTN over V, right? So PV equals NKT, right? Or equivalently, the volume is NKT over pressure. So this is an equation that might be familiar to you from chemistry classes or other places. Right? This is commonly called the, written this way, the ideal gas law. Okay, so that is a law that describes the relationship between pressure and volume and temperature in an ideal gas. For some of you, you might be familiar with seeing it in a slightly different form, right? Some of you might be familiar with it as pressure volume is little n times R times T, where this little n is the number of moles. Right. So really, these two equations are equivalent, right? And the way to see that they're equivalent is if you take the version that I showed you and you multiply and divide by Avogadro's number. Right? So you have PV is N divided by 6 times 10 to the 23rd, right, equals 6 times 10 to the 23rd times Boltzmann's constant times temperature. Okay, and now here, right, this combination of the number of molecules divided by 6 times 10 to the 23rd, right, that is the little n, the number of moles. Okay? And this thing, Boltzmann's constant times 6 to the 23rd, right? That is R, the ideal gas constant that you might be used to. Okay, so these are exactly equivalent equations. It's just one is thinking in terms of moles and the other is thinking in terms of counting molecules. So those things are the same, okay? And what I am trying to show you here is that you can think of this law that might be familiar to you as the result of a minimization problem, right? That it's the result of minimizing a free energy, because in this course, almost everything is minimizing a free energy. And so this is also, right? And so this is also a case, right, where the volume, it could have lots of different values, but in fact, when the system is free to choose its volume, then this is the volume that it chooses. And the volume that it chooses is proportional to the number of molecules. It's proportional to temperature, that is the absolute temperature in Kelvin, and it's inversely proportional to the pressure. Let's see, I have a plot of that in Mathematica. Let me just briefly switch from sharing the whiteboard to sharing Mathematica. So I go to Mathematica. Here is a plot to show you what I was just sketching by hand, right? So in this plot, we have G versus volume, okay? So here, the G, I'm just writing negative log V plus pressure over KT times V. So this is really G divided by the number of molecules and divided by KT. And so here you can see there's this logarithmic decrease, and then for large volume, there's a linear increase. And in between, there's a minimum somewhere. And that minimum is the optimum volume, which the system will select. Okay? And here's the nice interactive version of that plot with adjustable sliders for pressure and temperature. Okay? So you can see if I increase the pressure, then the optimum gets shifted to smaller and smaller volumes. If I decrease the pressure, the optimum goes out to larger volumes. And the same sort of thing with temperature, right? If I increase the temperature, the optimum goes out to larger volumes. If I decrease the temperature, the optimum goes to smaller volumes. So the system could have different volumes. You know, you might imagine it's even having little fluctuations of the volume around that value. But the optimum, the equilibrium, is going to be whatever is the minimum of this plot. Now, in physics, whenever you have a minimization problem, you can regard it as a fight between two things, right? A competition between two physical mechanisms. So one physical mechanism favors big volume, the other physical mechanism favors little volume. And then the competition between them makes a certain compromise. Right? So in this case, you can think of it as a competition between pressure and entropy. Right? So the pressure favors a small volume. Right? The pressure is pushing in. It is trying to make the volume as small as possible. Right? The entropy favors a big volume, because when there's a big volume, there are lots of possible states. There are lots of possible places to put the particles, okay, and put the molecules, right? And so when you have the competition between pressure and entropy, there's a compromise. And this minimum is what makes the best possible compromise between those two things. And then, well, so here in my high-tech illustration with the bag, right? If I make a bag and then, you know, there's a pressure pushing in, there's the entropy pushing out, and, you know, it's a real thing, right? Entropy is real. It just hit me in the head, right? And so, you know, that's you know, a way to visualize the competition between those two effects. Quick questions about this in general? No, no questions. You guys are happy with that. All right, good, good. Okay, so again, to speak of the analogy with the magnet, right? With the magnet, right, we have a competition between, when there's no interactions, we have a competition between magnetic field and entropy, right? That the magnetic field favors a big magnetic order parameter. Entropy favors zero magnetic order parameter, right? So it's a fight between those two things. So here, the analogous thing is between the pressure and entropy. Now, there's one more variation on this problem that I want to show you, dealing with non-interacting systems, and then I'll go put interactions in. Okay. So if I go back to my iPad, you know, when we had the magnet, right? It was nice and easy to do the non-interacting magnet, right? And then we had to make approximations in order to deal with the interacting magnet. That was a much harder problem. Okay. Here, it's the same kind of story. We can say, you know, if there are interactions between molecules, that is very difficult. That's what I'm going to talk about shortly. Okay. But what's easier than that would be an interaction between each molecule and gravity. This is not bad. Okay, so if you have an interaction, you know, of gravity pulling downwards on each molecule, that doesn't have anything to do with the molecules interacting between each other, right? That's a single molecule kind of effect, right? This molecule feels gravity, this molecule feels gravity, this molecule feels gravity, right? Each molecule individually feels gravity. And so let me show you how you would deal with a problem like that one. Okay, so let's go back to working out the energy of a state and the partition function. Okay, so if I'm dealing with interaction between each molecule and gravity, okay, so this could be like a simple model for the atmosphere, right? So the atmosphere has lots of oxygen and nitrogen molecules floating around, and each one feels the Earth's gravity. Okay, so let's assume a flat Earth, and each molecule is at some height, Z1 for molecule 1, Z2 for molecule 2, etc., right, above the surface of the Earth. Okay. So now we have the energy for each state, and that is the kinetic energy that we had before plus potential energy. Now, the potential energy is the gravitational potential energy, or the molecule in the Earth's gravitational field. So the kinetic energy is still the sum over all the molecules of the momentum squared over 2m. Right. Now, the potential energy is the potential energy for each molecule at a height Zi, okay, for molecule I. Okay. So this makes the mass of the molecule times the gravitational field times Zi. So all of that is in the sum. Okay. So this is now the energy of a state, which includes a potential energy term. Now, suppose we want to do the partition function. Okay. So just as before, we have a partition function, which is 1 over n factorial and Planck's constant to the 3n. And now I have an integral over all 3 components of the position for particle 1, and the integral over all 3 components of the momentum for particle 1. And the same for particle 2. Particle 2. And the same for particle 3, etc. Okay. And then the thing that has to go in the exponential is minus energy over kT. So it's minus this sum over all the molecules of the pi squared over 2m plus mg Zi all over kT. So it looks complicated, but actually we can do it step by step, the same as we did on Monday for no gravity. Right? So if we want to do it step by step, the thing to notice is that this exponential factorizes. That is, it is the product of something for particle 1 times something for particle 2 times something for particle 3, etc. Right? So it's e to the minus p1 squared over 2m plus mgz1 over kt times the same thing for particle 2, e to the minus p2 squared over 2m plus mgz2 all over kt times the same thing for number 2, for number 3, number 4, et cetera, right? So that is very, very helpful for us, right? Because now we can put the integrand for each particle in with the integral with each particle. So we get 1 over n factorial h to the 3n. And then we have an integral over all 3 components of R1, all 3 components of P1. And what we're integrating is the thing that depends on R1 and P1. So it's this exponential of minus P1 squared over 2m plus mg z1 over kt. Now we have to multiply this, right? We still have the integral over R2 of the same exponential for R2, right? And the integral over R3 and P3 of the same exponential for those variables, right? But these integrals are independent of each other, right? That unlike typical multiple integrals, they don't affect each other, right? And so, we could put parentheses around them. It's this integral times this integral times that integral, etc. Now we can look at the integrals and say, oh, they're all exactly the same as each other. So this then just gives us a power. We have to say n factorial h to the 3n. Now we just have this integral for R1 and P1. Plus mgz1 over kt, right? We have this integral and all the others are copies. So it's just all that raised to the n power, okay, where n is the number of molecules again. So now this is a question.
Is that assuming that all particles are the same height over
No,
the ground?
It's assuming all particles have the same mass and that they all have the same, experience the same gravitational acceleration, right? But particle 1 has a height z1, particle 2 has a height z2 is in here, right? But we're integrating over z1 and z2, right? This d cubed r1, this is dx1, dy1, dz1, okay? So we have some integral dz1 of this thing with z1. And then we have an integral dz2 of this thing with z2.
Yeah, that's exactly why I'm asking. So then why are we able to put the entire thing to the power n if z1 and z2 could be different?
Oh, well, it's just like if you have, an
we can do that
integral dx1 of e, I don't know, what's something that's easy to integrate, of, I don't know, e to the minus x1 squared, integral dx2 of e to the minus x2 squared, right? This integral is a number. This integral is the same number.
I mean, in definite integral, it will be same, but in indefinite integral, it will not be same. And I think here we are talking
Correct.
about
The
definite
Gaussian.
integral from certain limit to certain limit.
Yes. Thank you, Bajaya. That is exactly the point. So this is one of these points of sort of arrogant notation where I assume everybody knows what I'm talking about, but they don't really. This is a definite integral, right? This is a definite integral from minus infinity to infinity, right? Yes. These integrals are all definite integrals, right? These are definite integrals over all possible R1 and all possible P1, right? And so that means all possible normally means from minus infinity to infinity, right? I'll hang on just a second, and I'll spell that out explicitly. Okay, so let me erase this stuff and write specifically what I mean here. Okay, this is an integral. So it's 1 over h to the 3 and n factorial. Right? I have an integral over all possible x1, y1, z1, etc. Okay, so that makes, and I'm writing it, I could write it like this: dx1, dy1, dz1, dpx1, dpy1, dpz1. And the thing that's getting integrated is e to the minus p1 squared, which I could write out explicitly as e to the minus px1 squared plus py1 squared plus pz1 squared over 2m plus mg z1. Okay, now I'm saying it's an integral over each of these variables, right? So I could write really 6 integral signs here. Each of these things is getting integrated over all possible values. First, let's think about the momentum integrals. For the momentum integrals, right? The momentum in the x direction, it could be any momentum in the x direction. It could be arbitrarily fast this way, infinitely fast this way, infinitely fast that way. Okay, so each of these momentum integrals is from minus infinity to infinity. Minus infinity to infinity. So all this to the end. All right, so now I can do those momentum integrals, okay? And this is just a Gaussian integral which I can look up, okay? And the answer for each of those momentum integrals is 2 pi m kt to the 1/2, right? That is for the px integral. The same thing for the py integral. The same thing for the pz integral. So if I have all 3 of them, it's this thing to the 3/2 power. Okay, got those things. Check, check, check. Okay, now we still have to do the x integral, the y integral, and the z integral. Okay. Let's talk about the x integral. Remember, I'm assuming a flat Earth. Okay, so this is in the flat Earth, this is x. This is x. So we can say, how big is the flat Earth, right? Well, let's say x goes from 0 to L, right? And likewise, y, the y coordinate goes from 0 to L. So the area of the flat Earth is L squared. Now, when I go to do the x integral, that's going from 0 to L, right? All possible values of x. Okay. So I have an integral from 0 to L dx1 of something which doesn't have any x's in it, right? You look here, no x's, right? So it's constant with respect to x. So that integral just gives us a factor of L. Okay. Now, let's do the y integral. Okay. Once again, the y integral runs over all possible values of y from 0 to L. So it gives another factor of L. So that's L squared, right? Or this is the area of the flat Earth. Okay, now all that's left is the z integral, right? In the thing that I did on Monday, I would have said z also goes from 0 to L, right? And then I would have L cubed. And then that's where the volume comes from. That's where the volume came from in the thing I did on Monday. But now there is a dependence on z. It's because of gravity right there. Right? So I have to do a little bit of work for what is the gravity, what's the z integral? Okay. First of all, I could say, what are the possible values of z? Well, there's a minimum value of z, which is right on the ground, right? The molecules can't go lower than ground level. Okay? So the lower limit of integration is 0. Okay? But the molecules could go arbitrarily high. There's nothing that keeps molecules from getting to an arbitrary unlimited height above the Earth, right? So that integral will be from 0 to infinity. So I still have an integral from 0 to infinity dz1 of e to the minus mg z1 over kt, because I forgot the kt here. Okay, this stuff over kt. So I still have to do this integral. Luckily, it's not a really hard integral, right? It's just an ordinary exponential integral. But because I'm running out of time, I'll just copy it from my notes instead of doing it. But you can do it for practice, right? So this integral is equal to kt over mg. Okay. So this gives us the partition function with a system under gravity, okay? And mkt to the 3/2 L squared and then KT over mg to the n power. This this tells us something, right? I mean, this is now a tool that we can use to calculate stuff for the system of an ideal gas under gravity, okay? So what would we want to calculate, right? Well, a nice example of something to calculate would be what's the average height of a molecule. In particular, let's say, what's the average height of molecule number 1? It doesn't matter whether it's molecule number 1 or number 13 or whatever, they're all identical, okay? So what's the average height of molecule number 1? Okay, so the average of Z1, that would be the integral, right? Well, we have to do the general procedure for calculating an expectation value is it's this sum over all the states, or 1 over n factorial h to the 3n, blah, blah, blah. The integral over all the positions and all the momenta right? All of this times the thing that we want to average, which is Z1, times the probability of having that state, which is the exponential of minus the energy over KT divided by the partition function. Divided by the partition function, the thing that I calculated on the last slide. Now, when we look at this, we can say, oh man, the numerator has a huge number of integrals in it, but luckily, they're all the same as the integrals that we already calculated, except for one of them. Just the Z1 integral is different. Every other integral in the numerator cancels all the integrals in the denominator. Right? And so the only non-canceling integral is in the numerator, the integral dz1 over all the possible values of z1 of z1 e to the minus mg z1 over kt divided by the equivalent integral, the corresponding integral in the denominator, which I already told you is kt over mg. Okay. Now, the numerator is still an ordinary integral, like you could do in a first-year calculus class using integration by parts or whatever you want to do for integrals. And so once again, I'll skip ahead to the result, okay? And the result is that this ratio, so the average height of a molecule is KT over mg. So this is a number that we can calculate, right? And so for our simple model of the atmosphere, I could substitute in Boltzmann's constant. I could substitute in the temperature of 300 Kelvin. I could substitute in the gravitational constant, the 9.8 meters per second squared. Right? I could substitute in the mass of a molecule. For example, a nitrogen molecule, right? Because that's a common thing in the atmosphere. So for a nitrogen molecule, we have a mass in kilograms, whatever that is. I have it in my notes here, 4.6 times 10 to the minus 26 kilograms. Okay, so we get a height in meters, right? So this comes out to be 9.3 kilometers. Right? So that's kind of reasonable for what's the average height of a molecule in the Earth's atmosphere. It's what atmospheric scientists call like the thickness of the troposphere, the lower part of the atmosphere. And so, yeah, I mean, some molecules are lower than that. Some molecules are higher than that. But that's the average height of a molecule in the atmosphere. The point I want to make about this calculation, and I'll, hang on just a second, Jack. Point I want to make about this calculation, and then I'll stop for today, is that this is a calculation that has to do with thinking about one molecule at a time, right? Because these properties all factorize, right? That when we have our partition function, it factorizes into something for each molecule multiplied together. But on the next class, I'll deal with what happens if you have interactions between the molecules and how that becomes a much harder problem. So I'll stop and you guys can go if you need to. I'm sorry I'm over time. And Bijaya, I'll answer your question and anybody else's. Please.
Okay, so here our partition function is position dependent. So average height of the molecules may depends upon the kind of coordinate system we choose. I mean, if we choose spherical coordinate systems, then the expression may be a little bit different than kBt by mg, I think.
No. That's not a dependence on the coordinate system. That's a dependence on the assumptions, right? So you're saying, what if I assume a spherical Earth instead of a flat Earth, right? If I assume a spherical Earth, the answer will be a little bit different, right? But that's not because of a choice of coordinate system. That's because a spherical Earth is slightly different from a flat Earth. It's not very different, right? I mean, that's why I made an assumption of the flat Earth, even though I actually know that the Earth isn't flat, right?
No, I mean, in spherical coordinate system, if I need to integrate here, then there will be r squared dr. So
yes.
it might give a different expression because we need to consider gamma function instead of a normal exponential function.
Sure. Of course, but that's, I won't say that's because of the coordinate system. I would say that's because of the spherical Earth, right? The spherical Earth really is slightly different from the flat Earth. So if we had a spherical Earth, and then I would use a spherical coordinate system, okay? And then instead of integrating over x, y, and z, I'd integrate over r, theta, and phi, right? And the theta and phi integrals would be simple. And I'd have a more complicated integral over r, right? And the complicated integral over r would be both in the numerator and the denominator here, right? So I would get something, a little bit more complicated, in both the numerator and the denominator, and things, it wouldn't come out exactly like this, but it would come out very close to this, right? There would be some corrections which would involve, what is this length scale compared to the radius of the Earth, right?
Yes.
And the radius of the Earth is much bigger than this length scale, right?
Yes.
The radius of the Earth is thousands of kilometers, and this is 9 kilometers, right? And so I would get an answer which would be, instead of this thing, it would be this thing, plus some constant times this thing squared over the radius of the Earth. Right. So, I mean, I could do a perturbation theory in this ratio of this constant compared to the radius of the Earth. For sure, what I'm doing is just treating the flat Earth as if it's an approximation to a spherical Earth.